Hello everyone and welcome back. Today we're going to be talking about conditional logic and how to model conditional logic using flowcharts in Microsoft Visio. The learning objectives for this module include we will learn how to identify real-world selection structures, so that are related to conditional logic, and then we will create a flowchart that models conditional logic, including the single alternative, dual alternative, and case selection structures. As a reminder, here are the flowchart symbols that we will be working with in this course. So we have our start and stop terminators that are represented by ovals or the ellipse. We have input and output represented by the parallelogram, process represented by a rectangle. In this module, we're going to finally start to use the diamond, which represents a decision point. We have, of course, our flow line, and we will also introduce in this module the use of the connector. So how do we model simple decision making using flowcharts? We are going to look at several examples in this module, and we will start with the following example. So let's make a flowchart. A donut shop has asked you to design a computer application that determines the price of an order of donuts. When a customer orders a dozen or more donuts, they get a discount where each donut costs $1.25 instead of the regular $1.50 price. So just as we did in the first few flowcharts that we looked at, I'd like you to think about the input, processing, and output that need to take place in order for this application to function. So we will first have to prompt the user to enter the number of donuts that they would like to purchase. We will then have to decide, based on the number of donuts that they enter, how to calculate the total price. We will then have to calculate the total price and return the result back to the user. So let's go ahead and take a look at this example in Microsoft Visio. The first thing I'm going to do is drag out a square, and in that square we are going to again put the description of the application so that we have it well documented and can understand what the flowchart is supposed to do when we come back to it. So this application prompts a user for the number of donuts they will purchase and returns their total price based on decision criteria. Okay, so recall that we are first going to use the ellipse to draw the starting terminal for our flowchart. So we have our start. I will also copy paste this and create our stop as well. Okay, so remember that this application is a dance between the computer and the user. So the first thing we need to do is get from the user how many donuts they're actually going to purchase. So we can do that by prompting them using a parallelogram. So we can do this in the following way. We have our prompt. We can choose to write a whole sentence. I will keep it quite simple and just in the quotes put the word donuts followed by a colon. And then remember that we also need to choose a variable name to represent the variable that's going to store the value that we get from the user. So in this case, I will just simply use the word donuts and put that in the parentheses. Remember that we also have to create our legend as we go so that we know what each of the variables represents as we create them. So I'm going to go ahead and create the legend and add donuts as our first variable. So the donuts will simply represent the number of donuts the user is purchasing. Go ahead and connect our flow line. So now we are going to use our first bit of conditional logic, which means that we will have to make a decision. So if you take a look back at the slides, essentially when a customer orders a dozen or more donuts, they get a discount where each donut costs $1.25 instead of $1.50. So basically we're going to make a decision based on the number of donuts that they purchase. And we can use a mathematical expression in the decision point to help us understand how that decision is going to take place. So I'm going to pull out a diamond to represent our decision. And if we read the text again, it says when a customer orders a dozen or more. So we have to think about how to model this mathematically when we are programming. So we're going to use our donuts variable and simply put in the diamond donuts is greater than or equal to 12. We could also consider putting donuts is less than 12 and, swap the true and false sides of the decision. But for now, let's go ahead and do it this way. So we're checking to see whether or not the number of donuts that they entered is greater than or equal to 12. And based on the result, we will take a certain action. We will do a certain process. So I'm going to go ahead and put the flow line in. So this next bit of information is pretty important. When you have a decision point, you can only have two possible results from that decision. So either the condition is true or it is false. We do not have any other options in this case. And that gets into a little bit of theory of computation. So a computer cannot choose between more than two options. So if you've experienced something called case logic, which we're also going to talk about in this module, cases are actually just a series of binary decisions that are being made. So if it were possible for a computer to actually choose among more than two values, some very special things would take place in the world. So the way I'm going to model this is I'm going to double click the flow line, and on the right side I'm going to put what happens if the donut's value is true, that it is greater than or equal to 12. And on the left side, I'm going to put the process for if donuts is greater than or equal to 12 happens to be false. So you're welcome to swap the two. I just recommend being consistent so that you don't get confused as you're working. For me, I'm just going to keep true on the right always and false on the left always. Also be aware that every single symbol in the flowchart can only accept one flow line. And the only symbol that can have more than one flow line coming out of it is that of the decision. So and specifically, it can only have up to two flow lines coming out of it. And because of this, we're going to need to use connectors to make sure that we keep that flow line logic in place. So now we have our decision point set up. If donuts is greater than or equal to 12, we go back to the specifications and see that the customer will get a discount where each donut costs $1.25 instead of $1.50. So basically what we're going to do is, rather than calculate the total price based on $1.50, we will calculate the total price based on $1.25. And we will use a rectangle to represent the process when we do this. I'm going to go ahead and grab a rectangle, and on the true side we're going to create a new variable, which again is not absolutely necessary. You can certainly write this program without using a new variable to store the result, but in this case I think it helps us demonstrate the selection structure quite well. So I'm going to choose a new variable called total, and we will set total equal to donuts. If we think about the math involved, we're simply going to multiply the number of donuts that they're going to buy by that 125. And I'm going to go ahead and connect this to the flow line. I also need to make sure that I add the variable total to the legend. So the total is going to be the total price of the donuts. So now we have the process that occurs when this statement evaluates to true. We now need to add the process that occurs when the statement evaluates to false. So I'm actually just going to copy the process that we have on the true side and put it on the false side, and modify the constant here to be 150. So if we take a look at this now, we can see we start the program. It prompts the user to enter the number of donuts. The variable donuts is then used in the following conditional statement. So is the number of donuts greater than or equal to 12? If it is, we then calculate the total based on donuts times 1.25. If it is not true, we then calculate the total based on donuts times 1.5. The last thing we of course need to do is share the total with the user. So in this case, what we are going to do to bring these two flows back together, we are going to grab a circle that will serve as a connector. So the purpose of the connector is to ensure that the rules I was explaining about logic stay in place. So a connector can receive up to two different flow lines, but only one flow line can come out of the connector. In fact, every shape except for the decision can only have one flow line coming out of it, and a decision can only have two. So what I'm going to do is connect both of the processes to the connector to bring them back. This will allow me to insert the output parallelogram that will represent sharing the total with the user. And in order to do that, I'm going to grab another parallelogram and we will have our output. So the total price is, and I'm going to use the plus sign for concatenation again, and then append the total variable. So what this statement will do is display the text the total price is, followed by a space, and followed by whatever the value of the total is. So let me go ahead and connect the last two bits of flow. The last thing we needed to do was share the output with the user. So that is in fact the last step we need to do before we have our stop terminator. So take a minute to look over this flowchart. We have demonstrated here what is called a dual alternative selection structure, in which we have a decision that leads to a process when the condition evaluates to true, and also a process that occurs when the condition evaluates to false. So again, when you're making a decision, when the computer rather is making a decision, the result can either be true or it can be false. There are no other options there. So we cannot have more than two flow lines coming out of a decision. Notice again that the way that this flowchart is set up, that it is dynamic. So what that means is that regardless of what the user types in as input for the number of donuts, that it will always provide us with the total. You can also think about the flowchart in the following way. So you can consider that there is a little robot, and that robot is following the flow lines on the flowchart and performing each of the actions. So the robot starts here, prompts the user for the number of donuts, and takes the number of donuts as input. The robot then reaches the decision point and asks itself, okay, it evaluates this statement. Is the number of donuts that was entered greater than or equal to 12? If it is true, then the robot calculates the total based on donuts times 1.25. If it is false, it calculates the total based on donuts times 1.5. And then finally, it prints the total price is, followed by the total that was evaluated. Now, the other interesting thing here that you may not immediately consider is that we do have both of these processes visualized in the flowchart. However, only one of them will be visited by that metaphorical little robot. So, which means that really only one of these processes will actually take place when we're actually running the program. And that's an important distinction to make because it will help you understand how to test whether or not certain cases that you create are working, as well as put in statements in your program that allow you to test the functionality of your program. So again, while both of these processes are here, only one of them each time that the program runs is evaluated. And when you are working on your assignments, what I'd like you to do is consider, it doesn't have to be a little robot, but the testing really has to happen by you. So of course, once you get in front of a compiler, when you're actually coding, it will give you feedback about what your program is doing. In this case, you have to do that yourself. You have to sit there and walk through each of the flow lines and make sure that it is operating the way that you want it to operate. It's a difficult thing to do, I think, because it is completely theoretical, but it is extremely important. Now, there are a couple of modifications that we could make to this flowchart to improve it. For example, now that we have the power of the decision in our flowchart, we can start to talk about what happens if a user enters invalid input. So in this case, we're assuming that the user is going to put in a valid number of donuts and that the program will be able to operate without any problems. We'll leave this flowchart for now and come back to it and make that modification. I'm going to go ahead and save this as donuts, and I'll also put it on Blackboard. So now that we've seen how decisions operate in the flowchart, let's talk a little bit about the selection structure itself. So by the selection structure, I mean the decision point, so that diamond that helps us express what is called conditional logic. You may have heard of the term Boolean. So in this case, when we talk about Boolean expressions, we are talking about, for example, the mathematical expression donut is greater than or equal to 12, that will either evaluate to true or false based on what the value of donuts is when the program actually runs. So remember that every single computer decision will yield a true or false, yes or no, 1 or 0 result. There are no other options. Again, if there were other options, some very strange things would be possible in the world. At this point, you'll just have to take my word for it. If you'd like further reading on that subject, I can provide you some links to information about Alan Turing. And whenever we use a selection structure, we will invoke the evaluation of a Boolean expression to either true or false. These can be compound expressions, or they can be simple expressions, but regardless, they will be evaluated to true or false and allow us to either continue on with process or lead to another decision or terminate the program. There are 3 kinds of selection structures that we are going to visit in this course. The first is probably the one that you most likely think of when you're thinking about a decision, and that is the dual alternative or binary selection structure. So pictured on the right here, you can see that we have the flow line entering the diamond that represents the decision. On the right side, we have what happens if the condition inside the diamond evaluates to yes. So we have the process that leads from the yes evaluation over here. On the left, we have what happens if the condition in the diamond evaluates to no. So we see that we have a process on both the yes and the no side of the decision, hence dual alternative. So this means that regardless of whether the condition is true or false, we will take some action. There is also a single alternative selection structure, and in programming, and I think just in day-to-day life, this may not be one that you consider as often, but perhaps it is, that there is only an action provided for one of the outcomes. So in other words, there is a process, but that process is either on the yes or the no side of the decision. An example of this might be, okay, if it is raining, if that evaluates to true or yes, then I will pick up my umbrella, and if it is not raining, I will take no action. While we are not coding yet, we can talk about the syntax and how it applies to how we read and interpret a flowchart based on the type of selection structure that we have. You may have seen this syntax already. What we are talking about is if, then, else. So in the case of the single selection structure, in other words, when you only do a process on one side of the decision, we use if, then. So if it is raining, then I will grab my umbrella. In that case, there is no else clause. So we have if some condition is true or if some condition is false, then we take some action. And there is nothing that occurs in the opposite case. Else is invoked in the dual alternative structure. So if, for example, we use the donut example, if the number of donuts is greater than or equal to 12, then we calculate the total based on $1.25. Else, we calculate the total based on $1.50. So I realize the statements here are saying that for if then, it only occurs if the decision is true. More specifically, it is only evaluated in one case. That decision can be evaluated in multiple ways depending upon what kinds of operators you're actually using in the decision. And we'll talk about that in the next module. So we've already talked a little bit about variables and that variables can have different types. But we haven't really gone into detail about what kinds of variables we can have since we're not coding just yet. However, we have already worked with integer variables in the sense that, for example, if somebody's ordering a number of donuts, we would probably expect them to order whole donuts, and this would be a numerical value. We can also consider variables that are what we're going to refer to as string variables, or variables that are treated as text. So of course you can have a number that is treated as text, as well as letters of the alphabet, characters that are treated as text. Those will be stored in quotes. The reason for making the distinction is that we can use certain relational comparison operators with certain types of variables. In the case of the numerical variables, like integers and numbers that have decimals or fractional parts, we can use the equivalency operator or the double equal sign. So in other words, we could say, okay, is donuts equal to 12? We would use this double equals in our diamond if we were going to use that as our decision point. That statement would evaluate to true if both sides of the equal sign were equal. You've likely already worked with greater than and less than as well, which can be used with numerical variables also. So the double equal sign can also be used with string variables, and based on the programming language, it can evaluate in different ways. For our purposes in the flowchart, we will simply consider if we ask them to input, say, the text of yes in a certain case. If that is what we are looking for and it is equivalent to that, then it will evaluate to true. Once we get into the syntax, that may change slightly, but for now, just remember that you can use the equals with both string and numerical variables. Greater than or equal to and less than or equal to, which are written thus, can also be used with numerical variables. So the distinction here is that you are being inclusive in the operation here. So for example, like in our donut example, is the number of donuts greater than or equal to? So it can also be equal to 12. You may recall using a number line in early education with a filled in circle to represent that that number is included in the interval. What you are looking for in specifications in the text are things like at least. So at least will refer to greater than or equal to, or for example, at most would indicate less than or equal to. If we are using the language of greater than or less than, we would just use the strict operators or the exclusive operators. Finally, this may not be an operator that you've seen before, but we also have a not equal to operator, which is the less than and greater than symbols put together. So statements like donuts is not equal to 12 evaluate to true when both sides are not equivalent. So we can use this operator with strings and numerical values as well. So the next question we need to answer is, how should our applications respond when they receive input that does not make real-world sense? So we are going to take another look at the donut application that we just made and see if we can come up with a couple of cases of invalid input that a user might put in, and see if we can revise the logic to make it so that the program immediately terminates when given invalid input. I will say that we will discuss input validation further once we introduce the concept of repetition and loops, when we can actually handle input validation in a different way so that we can reprompt the user to input a value. Since we don't have repetition at this point and we only have conditional logic, we are simply going to revise our flowchart so the program terminates when given invalid input. So let's take another look at the donut price example. We need to alter the flowchart for the scenario so that if a system user enters a value that doesn't make sense for the number of donuts, that they get an error message and the application stops running. So the first thing we should think about is, okay, what kinds of invalid input can a user actually put into the program? So as I mentioned previously, we would like to make sure that the customer puts in a value that is at least 1. There are ways that we can use math to make sure that they do enter an integer. We won't handle that case right now, but we can certainly write a flowchart that handles that kind of invalid input. In this case, we're going to just make sure that they put in a value that is in fact greater than 0. Another case might be that they input a value that isn't able to be processed using the mathematical operator. So for example, some programming languages will not be able to process text in a mathematical expression. So if they entered the word name, for example, and we tried to do is name greater than or equal to 12, it kind of depends on the language as to what will happen there. This is also a case that we're not going to consider at the moment. For the moment, we're just going to consider the case that we want them to put in a value that is greater than 0 for the number of donuts. So we're going to return to the original flowchart and see if we can simply modify it. I am actually just going to save as, and I will call the new file name donuts invalid input. And so I would like to encourage you to consider when you can reuse flowcharting logic. So the purpose of talking more in detail about the different kinds of logical structures is so that when you recognize that logical structure, that if you already have one in place, that you can just reuse it and change the variable names and the mathematical expressions involved. So we happen to have a dual alternative selection structure here. If you ever need another dual alternative selection structure, you can refer back to this flowchart that you've already created. So let's revisit this. We need to alter the description first because we're going to do some kind of invalid input handling. I'm going to add a sentence at the end that simply says, if the user enters a number of donuts less than 1, the application provides feedback and terminates. Okay, so thus far we have our start of the program and we prompt the user for the number of donuts using our parallelogram. Now we have to consider, okay, where are we going to put this input validation? We already have one decision point that considers whether or not the number of donuts is greater than or equal to 12. There are a couple of different ways we can approach this problem of making sure that the number of donuts is in fact greater than 0. We could put a decision point before this one that asks, okay, is the number of donuts greater than 0? And then proceeds to ask, okay, is the number of donuts greater than or equal to 12? But if we think about it, if the number of donuts is in fact greater than 12, we know that if that's true, that the number of donuts is also greater than 0. If we take a look at a number line, 12 is obviously greater than 0. So if this condition is true, the condition of valid input that we are wanting is also satisfied. So there's no need to check to see whether or not the value of the variable donuts is greater than 0 after we verified that it is already greater than or equal to 12. With that in mind, we can realize that in the case that the number of donuts is not greater than or equal to 12, so if we take the false branch, then we should also check to see if it is greater than 0. And based on that, we can add logic to write a message to the user that they've entered invalid input and then terminate the program. And then we can also address the process needed for the case where the number they entered is between 0 and 12. So what I'm going to do is this. I'm going to get rid of the logical flow line there, and I'm going to detach this logical flow line so that we can actually add different logic. Okay, so again, in the case that the number of donuts is greater than or equal to 12, we can simply take the original true branch. We don't have to then verify that it is also greater than 0. This evaluates to false, however, we now need to also check to see if the variable has a value that is greater than 0. So what I'm going to do is actually copy the decision point, and in this new decision, I'm going to check to see whether or not the number of donuts is greater than 0. So strictly greater than, because if it is strictly greater than, then it will be assumed that it is 1 or greater. There are obviously some other cases that we could handle here to make sure that it is also an integer, but we're going to keep it simple for now and just demonstrate how this branching logic works. So what I'm going to do, first of all, I'm going to drag the description down. So we're going to have a little bit longer flowchart here. I'm going to apply the false branch once again to the first decision point. So the first decision point still has a true or a false branch, but the false branch is actually now going to connect to this second decision. So what we're actually doing here is nesting decisions. And again, every single decision either evaluates to true or false. So it will take on one of those Boolean values. So similar to this decision, this second decision is donuts greater than or equal to 0. We'll also have a true and a false branch. So let's think about this. If the decision evaluates to true, so that the number of donuts is in fact greater than 0, what we want to do is actually just return to this process that we had originally. So we will want to calculate the total price based on the price that does not have the discount. So I'm going to draw a flow line to connect to that process and make sure I write true on the flow line. I'm going to then return the flow to the original connector that we had. We'll have to do a little bit more modification down here because we have another branch to evaluate, and we'll need to join everything up again with the connectors to make sure that the rule about the flow lines is in play. So if this condition is false, if the number of donuts entered is less than or equal to 0, and remember that if you are evaluating this kind of expression, in the true case, it is going to be strictly greater than 0. In the false case, 0 will actually be included in the values that are present. So in that case, we're going to keep this pretty simple. I'm going to grab another parallelogram, and we are going to output to the user. So our output will say, quite simply, invalid input. Again, we don't have any repetition at this point, so we're just going to simply tell them that they entered invalid input and terminate the program. So I'm going to add the false branch here and make sure I label it as such. So what needs to happen here is first I need to make sure that I am still providing the output necessary if the input was valid. So I'm going to go ahead and join the connector to the output parallelogram here that provides the total in the case that either the variable donuts held a value that was greater than 0 but less than 12, or that was greater than or equal to 12. So we'll join that back here. Then we also need one final connector to bring all of the branches of logic together to get to the terminator. So again, each connector can receive a maximum of 2 flow lines, and only one flow line can come out of the connector. So I'm going to join the logical flow to the connector here out of the invalid input message and also from this output message here. And then I can join it to the stop terminal. So this is our revised flowchart for including a message to the user that their input is invalid if they enter a value for donuts that is less than 0. And before we revise the flowchart, we thought a little bit about how to be efficient given what we know about the number line. So if we check again to see if the number of donuts is greater than or equal to 12 and we find that to be true, we do not then need to also check to see if it is greater than 0. We know that it is greater than 0 and we can proceed accordingly. If it is less than 12, however, we do have to then check to see if it is greater than 0 or not. And if it is greater than 0, we proceed to calculate based on the original price. If it is not, we tell the user that they put in invalid input and then terminate. And again, I'd just like to reiterate that we were able to take the original flowchart and just make some simple modifications in order to include this other piece of logic. I will also post this one to Blackboard for your reference. The last example that we are going to work through in this video is that of deciding among cases. So again, I mentioned that it's tempting to think that a computer can choose among several cases, and it can. However, you have to understand that it is still making a true or false determination. It's just making a bunch of true or false determinations in rapid succession. And we're going to take a look at an example to see what that looks like in a flowchart. Let's take a look at the following example. A professor has asked you to create an application that assigns letter grades based on the number of points a student has earned at the end of a course. Letter grades are assigned based on the following scale. 90% and above earns an A, 80% up to 90%, not including 90%, earns a B, 70% up to 80%, not including 80%, earns a C, and students that earn below 70% receive an F. Additionally, we know that the total number of possible points in the course is 1,000. So when reading this problem, we start to understand that we have several cases that we need to check to see which letter grade a student has earned in the course. And just like the other problems we've already looked at, there are multiple ways of setting this up, multiple ways of getting a correct solution. So we could, for example, begin with the highest letter and check to see whether or not they've earned an A, then check to see whether or not they've earned a B, then check to see whether or not they've earned a C, and so on. We could also work in the opposite direction, so check to see if they have earned an F first and go from there. And I'd like to encourage you to consider all of the possibilities, because by doing so, you'll be able to see which one is most suitable. What you're going to see in this problem is that we have multiple decision points that lead one right into the next, up until the point where we have a default case, in this case that of receiving the letter grade of F. The other consideration we have to make in this problem is how to get from a number of points to a percentage, which in this case is pretty simple because the total number of points possible is 1,000, and we can get from 1,000 to 100% fairly easily. So let's take a look at how to create this flowchart in Microsoft Visio. Again, the first thing I'm going to do is drag out a square so I can write up a description. In this case, we are going to say, so this application takes the number of points a student has earned in a course out of 1,000 and returns the letter grade they have earned. Now I have simplified the different letters just for the sake of limiting the space that we're using in the flowchart, but of course we could expand it to include the letter D as well if we wanted to. Next thing I'm going to do is bring out my ellipse and create the start and stop terminals. So the next thing I'm going to do is again consider how the application will flow. The first piece of information I need is how many points the student has actually earned in the course. So the first thing we're going to want to do is probably prompt the user to enter the number of points that they have earned. To do this, I'm going to grab a parallelogram and write out the following prompt. Points earned, again, just keeping it very simple. And we would like to store the number of points in a variable. So I'm going to call this variable earned. I'm going to go ahead and create the legend and add the variable earned to the legend. So this will be the points earned by the student. Go ahead and connect our first flow line to the input. Okay, so now we begin the decision-making process. And again, the purpose of this example is so that you can see what a case structure looks like in a flowchart. So we do have several cases here. We have the case where they earn an A, where they earn a B, where they earn a C, or they earn an F. And this is based on a percentage. We have to keep in mind that we'll need to calculate first what percentage they've earned based on the number of points that they've earned out of 1,000. So before we actually get into the cases, I think what we should do is bring out a rectangle and go ahead and get the percentage that they've earned out of 1,000. Now we could, at this point, if we wanted to make the program a little bit more dynamic, create a constant variable to hold the possible number of points in the course, or that would be 1,000. I'm going to forego that for the moment and just hard code the 1,000 into the process. So we will also want to introduce another variable here, and I'm going to call that percent. So percent is going to be equal to the number of points earned divided by, in this case, 1,000, which again, I could make a separate constant variable to hold the total possible number of points. I then need to multiply the result by 100 to get the percentage. So I can see that if, for example, the student earned 900 points out of 1,000, you would have 0.9 times 100, you would get 90%. Let's go ahead and add percent to our legend as well. So percent is going to be the percent earned by the student. Go ahead and connect our flow line to the process. Okay, and now that I have the percent is going to be the variable that I check to see which case is actually invoked. So in a case structure, what we want is once we hit the appropriate case, we want to exit the decision-making logic because only one case is going to be met. So in other words, if a student earns a B, they will not have earned an A, a C, or an F. It will be completely exclusive to that B. So let's go ahead and bring out a diamond to see how this flow will work. So what is our first case? I suggest that we start at the top of the scale and work our way down. Because if you think about it, going back to the number line, if they have earned a 90% or greater, then of course they will not have earned something less than that, and we do not then have to check for that as well. So we're going to check whether or not percent is greater than or equal to 90 in our first case. I'm going to go ahead and connect the decision to the previous logic. And again, as with every decision, we either have a true or a false result of the evaluation. So I create the true branch on the right side. There are multiple ways that I can process the output. I can create a new variable that is assigned the letter that they've earned and then output that. I can also choose to display output in each case. It kind of depends on what you are trying to optimize. I think in this case, we will create a new variable called letter that will represent the letter earned by the student, and we will assign the letter its correct value in the case structure and then display the result at the very end before the stop terminal. So again, multiple ways of doing this. It is up to you to choose which way you would like to proceed. So in the case of true, for percent greater than or equal to 90, we are going to have another rectangle. So we're going to have a process that sets the letter equal to the letter of A. When setting up a case structure, it's a little bit more convenient to have the false branch come out of the bottom of the decision. Again, you're only going to have two branches, a true and a false branch, when you have a decision. So let me go ahead and add the false branch here. So in the case that percent is not greater than or equal to 90, I'm now going to check to see whether or not it is greater than or equal to 80. Just adjust my flow lines a little bit to clean it up. So now I have the true flow line coming out of the right side and the false flow line coming out of the bottom that leads into the next decision. If this condition evaluates to true, I'm going to assign a letter of B. So you can see that Visio offers to automatically connect you to another shape. So I'm going to take that offer and connect to a rectangle. I'm going to put it in line with the previous rectangle and set letter in this case equal to B. I'm going to adjust my flow lines a little bit just to clean up the diagram and add my true title to this branch. We'll see how to reconnect each flow when we're finished with each case. Next, we're going to check to see whether or not percent is greater than or equal to 70. So let's go ahead and add another branch down here, the false branch that will lead to check whether or not percent is greater than or equal to 70. Go ahead and connect that and add the word false. In similar fashion, we're now going to add the process of letter equals C. If percent greater than or equal to 70 evaluates to true, add the word true. Now the last case we need to check is whether or not the percent earned is less than 70. And we can also consider in this case what would represent valid input for this application. We have not handled invalid input. Again, we don't have repetition yet, so we're not doing that at this moment. However, we can at least base our default condition, which that's what we're going to call it when we're talking about cases, the default case being the case that is invoked if no other case is true. In this case, that would be whether or not % is greater than or equal to 0. So it is possible that the student did not do any of the work and thus earned a grade of F based on point of 0. I'm going to go ahead and drag the stop terminal down so that we can add our default case. So if % greater than or equal to 70 evaluates to false, we have our default case at the bottom, and this will check whether or not % is greater than or equal to 0. Because we are dealing with a number line, this case will be invoked if the user put in valid input and it did not evaluate to any other case. So let's go ahead and add our process to set letter equal to F in the default case. Go ahead and connect our true flow line. Now the last thing we need to consider is how to share the output and how to gather up all of these flow lines so that they connect to one another using connectors and reach the stop terminal. So regardless of what happens during this decision-making process, letter is assigned a value. And this is based on the math that is involved and the assumption that valid input was put into place in the logical flow. Thus, we can assume that one of these 4 true branches was taken. So in other words, we're not going to have a case where % is in fact less than 0. If we were to consider that case, we could add a message that says that the user input invalid input if we wanted to, or we can just reserve that for another diagram. We should, however, regardless, add that false branch because every decision needs a true and a false option. So the way we're going to connect all of these may seem a little tedious, but we want to follow the rules of the flowchart design. So I'm going to grab a circle that represents a connector in order to help us connect all these flow lines back together. So I'm first going to connect the letter A option to the connector, connect letter B to that connector. So I'm going to have a connector circle for each result, each case, and connect down like so and across like so. We should then decide whether or not we want to handle invalid input, assuming that they entered a negative number, or just assume that they entered a number that was in fact greater than 0 and that was a number. Since this is our first round, I think we'll just assume that they did in fact enter a value that was greater than 0, so we won't give any feedback about invalid input. Instead, what we'll do is add one more connector because we have to get these logical flow lines back together, connect it to the false case down here, connect the final connector here, and then finally, we can share output with the user. So I'm going to go ahead and grab that parallelogram again, and we will have output. We can choose to add some text in the output, or simply just share the grade. We go ahead and connect the flow line first, and then we'll say output. Let's add some text. So letter grade, colon, space, and then plus. And again, we are using the variable name letter, so that it is in fact dynamic. This will ensure that whatever letter is actually earned based on the case structure, that's the letter that's shared in the output down here. That was the last thing we needed to do in this application, so I'm going to go ahead and connect the final flow line to the stop terminal. See if I can zoom out to get the whole flowchart on the page. I can try to clean it up a little bit in terms of spacing, but this is what our flowchart for case diagram actually looks like. So you can see the case structure here. We have a set of decisions that lead into one another, specifically that connect via the false flow line. So these are disjoint cases that if they've earned an A, they have not earned any other letter grade. So this is the final example for this module. It is the final flowchart related to this kind of conditional logic. I'm going to go ahead and save it as grade cases and share it to Blackboard as well. So now that we've seen an example, let's talk a little bit more in depth about the case structure. So the case structure is a specialized selection structure. We already saw the dual alternative and single alternative structures. The case structure is designed like the example that we saw with the false branch from each decision leading into another decision. So we use this structure when there are several distinct possible values for a single variable. So that in this example, the student would only earn one particular letter grade and not the others. So in each value requires a different subsequent action. Here is another example of the case structure for you to look at. There are two possible options for setting this up in a flowchart. We used the option on the left where we have one decision that leads into the next, and so on until we hit the default case. You can also choose to set up the case structure like the flowchart on the right here, where we do have each of the cases indicated by the number underneath the decision. However, I actually don't particularly like how this is set up because it gives you the false impression that the computer is actually able to choose among cases rather than simply making several binary decisions in a row. So I'd encourage you to stick to the format on the left. So please take some time to work through the examples in this video and let me know if you have any questions.